Welcome to my talk, How Would I Learn Cost Models Really? Insights for Query Optimization Tasks. This is joint work with my colleague Manisha, Johannes, Harald, and Carsten. Cost estimation is crucial for databases. If you look into certain problems in database systems such as query optimization, resource allocation, query scheduling, or index administrative view advisors, they in fact all highly depend and benefit from precise cost estimates. Cost estimates are typically obtained by having a query plan that is fed into a cost model, which then in turn provides cost estimates, such a runtime here in this example of 240 milliseconds. And so far, cost models were built with handcrafted cost functions, which are typically rated sum of different parameters defined in the optimizer. However, these traditional cost models often misestimate cost and thus reduce an optimization potential in these tasks above. So research agreed on that we need more accurate cost models. Overall, this led to the rise of learned cost models. And here, the idea is to use machine learning to learn from previous query executions in order to predict runtimes more precisely. Overall, this is in fact a hot research topic, as we saw many recent papers in SIGMOD, VLDB, or ICD over the last years. And the good news is that learned cost models are able to provide highly precise cost estimates. Today, I will focus on the task of query optimization, which is fundamental for every database. And here, cost models play a crucial role. Let's now have a look into this. So query optimization, we typically have a SQL string that we want to optimize. And for this, we would come up with different plans that we iterate over. For instance, we have a nested loop join or hash join in the query plan. We now want to select the fastest plan. So these plans are fed into a cost model that then predicts us the runtime, for instance, 240 milliseconds or 82 milliseconds for the hash join, which would be here the faster plan and thus the better selection. So we can agree on that precise cost estimates are crucial. And the question is now, how do learned cost models actually help here, given their better accuracy, and how can they support query optimization? And this brings me to the title of this paper, which is How Good Are Learned Cost Models for Query Optimization? We saw already and discussed this that learned cost models are more precise. And the question is, what does this precision give us and what's in it for query optimization? Unfortunately, the numbers don't yet look that very good when we optimize queries because learned cost models actually provide a higher runtime when we use them in query optimization. To better understand and more systematically address this, we dissect query optimization in this paper by analyzing three important subproblems, which are join ordering, access path selection, and the join operator selection. And today I only can talk about task 1 and 2, and for the third, please have a look into the paper. However, they are all fundamental for query optimization. Before actually now looking at the numbers, let's first set the stage. In our paper, we could not evaluate all available models as there are just too many, but we selected a set of representative models that reflect the diversity of approaches and also come with published code. In our paper, we compared 7 state-of-the-art models, which you can see here on the slide. I will now guide you through the main dimension of learned cost models to give you a better understanding how they actually work. One dimension is the plan representation, which is flat or graph. And what does it mean? Flat models typically try to learn from the query graph in a flat form, for instance, by counting the number of operators, like the number of joins. Graph-based models, in contrast, try to learn from the graph by modeling its interdependencies, typically in the form of a tree or query graph. Next, we have the database dependency. And again, here we have two categories, which are database agnostic and database-specific models. Database-specific models are trained on one database and also can only predict for this same database. In contrast, database-agnostic models are trained on a broader set of different databases and then also can predict for unseen databases. Finally, we have a broad range of different model architectures, ranging from regression trees, deep sets, up to graph neural network and transformers. We compare our learned cost models against two baselines, which are Postgres 10 and Postgres 16. And we train our models on 200,000 selection, prediction, aggregation, and join queries that were operated on 20 different databases. However, we made sure that all models were trained on the same data per dependency class that I just presented. Finally, the learned cost models learn from a broad variety of different model inputs. And I can't explain all details here, but most important are the query plans, estimated cardinalities, table samples, database statistics, and Postgres costs, which are used as input to these models. Let's now have a look into the first task, which is join ordering. The question here is, which order of joins is actually optimal for a given query? And the requirement for a cost model is to identify the fastest join order. If we here look at an example for joining three tables R, S, and T, then we can see that different join orders clearly bring different runtimes. On the left, we have an optimal plan, which only takes 2 seconds. And on the right, we have a different join order, which is suboptimal and thus takes way longer, in this case, 28 seconds. And now we want to find the fastest join order with our cost model. Let's now have a look into example query. And here we have selected the query number 33 from the job light. This query has 4 different tables and 3 joins, and this results in over 1,000 join orders, which I will now present you. So in our study, we enforced all different join orders for the query execution, but let the optimizer select the remaining parts of the physical plan, like the selection of physical operators. Here now you can see all of the join duration on the x-axis and on the runtime on the y-axis. And we sort now all of the join orders according by their runtime in an ascending order. So on the leftmost plan is the fastest join order, which we ideally wanted to select, and the right end is the slowest join order with the highest runtime. And clearly there would be even more join orders. However, we need to time out at some point because otherwise this experiment would be just too expensive. And the leftmost is now the fastest plan that we want to get with learned cost models. And overall, learned cost models should moreover be able to understand this black curve by predicting very similar values. So we now took every model and analyzed their predictions. First of all, Postgres. And Postgres overall is doing a maybe acceptable job. So in the middle, it's more or less precise. But if you look at the more extremes, it does not get the trend fully. And in addition, it also has different spikes. So overall, it could be better, but overall, it also gets the trend to some extent. Now let's look into the learned cost model. How do they actually behave? And if we look at this, they are actually way more noisy. And some learned cost models are overestimating by a large factor, some are underestimating. And overall, on the first impression, no model is doing it actually very well. However, we can also see that the learned cost models are more of than Postgres. To describe this more quantitatively, we propose in our paper novel metrics, which is the selected runtime, which gives us the information of how fast is the selected plan. And this you can see at the green example. So there the prediction is minimal. So this would be the plan that the green QPP-net cost model selects. And this is clearly not optimal, but has a way higher runtime than the optimal plan. Next, we also propose to surpass plans and way more metrics. And this metric tells us how optimal is the selected plan in percent. So the plan that the green model would select roughly outperforms 40% of all the plans by its selection. Okay, but how are the numbers now on the full data set? And this is what we did. We have now this job light benchmark where we have this exhaustive join generation strategy, and this covers 70 queries with up to 4 joins, resulting overall in over 23,000 plans. We now look into the selection of the models. And here you can see first the selected runtime. The black curve, or the black line, represents the optimal runtime. If every model would always select the best plan, then this would be the optimal runtime that we could obtain in this data set. However, no model is clearly able to always select the best queries. Still, we can see that in fact Postgres on the very left selects the fastest plans and actually outperforms all cost models. And similarly, if we look at the surpassed plans metric, which should be ideally high, we also can see that Postgres on the left typically has the highest values of up to 100% for many queries. This means that it often selects the most optimal plans. So overall, we can see that in this task, traditional models are still outperforming learned cost models for the task of join ordering. But how is it for different or other tasks? I briefly now want to talk about the task of access path selection. And here we discuss it's about how to optimally access a given table. So the requirement for a cost model is to decide between a sequential scan and an index scan. For example, we now want to find an optimal access path for this query, which is select star from title where production year is larger equals 1992. And we either have a sequential scan, which would be fast for many qualifying tuples, or an index scan, which would be fast for few qualifying tuples. And actually deciding between those is not easy and not trivial, but challenging for cost models. And this clearly depends on the selectivity. For that reason, we now change the selectivity of a single column for this very same example query where we changed the production year increasingly. And by that, we also change the selectivity. Let's now look first into the real runtimes. And here we can see if we increase the selectivity, so we select more and more tuples, then clearly the runtimes increase for the index scan, which is the dashed line, and for the sequential scan, which is the solid line, both. However, we can also see that for small selectivities, the index scan is faster by selecting by faster retrieving tuples, and for the higher selectivities, the sequential scan is faster. So overall, this is reflected in this green curve, which would represent the optimal selection, and this is exactly what the learned cost models should be basically give us. We iterated now in 10% steps through the space and asked the models for predictions and show you the selections in the following. And each cross here marks a single prediction, first of all for Postgres. Overall, Postgres is doing a decent job. Most of the time, select the sequential scan. For the small selectivity case, the index scan. But overall, it's not too bad. How do the learned cost models behave now? And here we can see that the brown model fat vector, the green QPPNet, the blue query former, and the pink zero shot all of the time select the index scan and never, in fact, select the sequential scan. Other models, such as end-to-end, are more noisy. In our paper, we repeat this, of course, over different columns on different datasets. But overall, we see that Postgres again outperforms learned cost models for access path selection. And we also found that learned cost models often prefer index scans and have a bias towards indexes. Let's now have a step back. The question of this paper is how good are learned cost models for query optimization? And we looked into these three tasks that I just mentioned. Overall, we saw in our paper that classical approaches typically still outperform learned cost models in all tasks. In some cases, they are on par. And one reason that we found is the training data bias. Overall, we saw that learned cost models prefer indexes for this access path selection, for instance, but also in terms of nested loop joins for the join operator selection. Why? Because they learned to be always fast. And this comes from the fact that learned cost models learn from pre-optimized plans only in traditional training strategies. I will talk about this a bit later, but this is one reason that we found. The question now, is this actually the end of learned cost models? Why should we use learned cost models at all? And in our paper, we argue that we should use learned cost models at all. Why? First of all, traditional models are still off and come with certain limitations that we already discussed in the beginning of this talk. Next, learned cost models are able to provide highly accurate estimates that are useful across a broad variety of tasks and not only query optimization. Next, finally, learned cost models are not yet optimized for query optimization. And this brings me to the question, how can we now actually fix learned cost models? The first recommendation of our paper, and we have way more, is to look clearly at the downstream task, which is the plan selection. So far, learned cost models focus on accuracy and demonstrate that they can predict query executions highly precise. However, this is not enough. For query optimization, we also need to address the ranking capabilities of models. And in fact, both properties are equally important. And to achieve this, we propose novel metrics that you can use to evaluate your model and train your model against to have the downstream task in mind. Next, we propose to overcome the training data bias that I just mentioned. And the downside of existing works is that they only learn typically from pre-optimized plans. So plans that were already executed once by the database, and thus they were also optimized by a database optimizer. And so the learned cost models only see optimized plans. Importantly, we also now need to learn from suboptimal plans. And we did this in the paper, so where we do a fine-tuning experiment where we learn from good and bad access paths. And overall, you can see here is the runtime of the experiment of all the certain learned cost models before the fine-tuning. And here you can see this Postgres and ZeroShot are the best, but no model is still able to outperform Postgres. However, if we now fine-tune the learned cost models with bad access plans, they get a better understanding of access path selection. And in this case, the runtime decreases for all models, and we are finally able to beat Postgres when using the zero-shot cost model. By following the ideas of our paper, we believe that learned cost models can be made practical for query optimization. It's, however, not a trivial but challenging task. And for this reason, we are looking forward for the ideas of the community to future improve learned cost models. With that, I'm at the end of my talk, and I'm happy for questions. In this case, please write me an email. Thanks for your attention.